Welcome to this scientific lecture on one of the most fascinating problems in thermophysics and baking science, the mystery of Neapolitan pizza browning. Let me start with what we expect to happen. When you place pizza dough in a very hot oven, basic physics tells us the browning should be relatively uniform. According to classical heat transfer theory, conduction through the dough should produce smooth, gradual browning across the entire surface. Fourier's law of heat conduction tells us that heat flux Q equals negative K times the temperature gradient. Here K is thermal conductivity. At the extreme temperatures used in Neapolitan pizza ovens, around 485 degrees Celsius or 905 degrees Fahrenheit, thermal diffusion through the thin dough should be very rapid. The thermal diffusivity alpha equals K divided by density rho times specific heat seepage. For dough, alpha is approximately 1.4 times 10 to the negative 7 square meters per second. Based on this physics, we would predict a smooth, uniformly golden brown surface developing gradually over time. But here's the paradox. Neapolitan pizza doesn't brown uniformly at all. Instead, it develops dramatic, irregular dark spots called leopard spotting, and explosive blisters form within just 60 to 90 seconds. These leopard spots are dark brown to black patches surrounded by lighter golden areas. They appear randomly distributed, not in any predictable pattern. Large blisters also form rapidly, expanding to several centimeters in diameter in just a few seconds. This is much faster than simple thermal diffusion would predict. So why does this violate our expectations? Let me explain the physics more carefully. The heat equation states that the time derivative of temperature equals alpha times the Laplacian of temperature. This describes pure conduction. If we assume steady-state conditions with uniform heating from all directions, the solution predicts gradual uniform temperature rise and therefore gradual uniform browning. The characteristic diffusion timescales as L squared over alpha, where L is the thickness. For 3 mm thick dough, this gives about 64 seconds. Yet we observe localized browning in under 10 seconds. Something is clearly missing from our conduction-only model. To solve this mystery, researchers used high-speed thermal imaging cameras to observe what actually happens inside a Neapolitan pizza oven. The thermal cameras revealed something crucial. The radiation field inside the oven is highly non-uniform. The dome radiates intense infrared energy, but in a spatially varying pattern. The dome creates hotspots and cold spots. Some areas receive intense infrared radiation, shown in red, while others receive less, shown in yellow. Radiative heat transfer follows the Stefan-Boltzmann law. Heat flux equals emissivity epsilon times the Stefan-Boltzmann constant sigma times T to the fourth minus ambient temperature to the fourth. At 485 degrees Celsius, radiative heat transfer becomes the dominant mechanism, not conduction. This is because radiation scales with the fourth power of temperature. The Stefan-Boltzmann constant is 5.67 times 10 to the negative 8 watts per square meter per Kelvin to the fourth power. The thermal imaging revealed intense localized infrared bursts hitting specific spots on the pizza surface. These localized radiation bursts can deliver 20 to 30 kilowatts per square meter to small regions, far exceeding the average heat flux. A typical burst delivers approximately 25,000 watts per square meter. This is enough to rapidly vaporize water in the dough. Remarkably, when researchers mapped the hot spots, they found they correlated exactly with where the leopard spots formed. Now let's understand what happens when these intense radiation bursts hit the moist dough. Pizza dough typically contains about 60% water by mass. When localized heating occurs, this water rapidly vaporizes. The latent heat of vaporization of water is 2,257 kilojoules per kilogram. This is the energy required to convert liquid water to steam. Steam pockets form beneath the surface. Because the dough acts as a barrier, pressure builds up rapidly inside these pockets. The ideal gas law PV equals nRT tells us that pressure P is proportional to temperature T for a fixed volume 5. Here's where it gets even more interesting. The pressure rise observed was much faster than the ideal gas law alone would predict. Let me pose a question. Why does the vapor pressure spike faster than a simple ideal gas calculation would predict? The answer lies in transient vapor pressure effects. When water rapidly vaporizes in a confined space, we can't use steady-state assumptions. The rate of pressure change, dP over dt, equals RT over V times dm over dt, where dm over dt is the rate of mass vaporization. The vaporization rate depends directly on the local heat flux from radiation. Higher radiation means faster vaporization and faster pressure rise. The mass vaporization rate equals Q rad times area A divided by latent heat L versus, for a 25 kilowatt per square meter flux on a 1 square centimeter spot, this gives 1.1 grams per second. Now let's calculate what happens when this steam pressure builds up. Pizza dough has a yield stress, the stress at which it permanently deforms, of about 1,000 to 2,000 pascals. When internal steam pressure exceeds about 2,000 pascals above atmospheric, the dough yields and a blister forms. Under intense localized radiation, this critical pressure can be reached in just 3 to 5 seconds. The blister expands rapidly as steam continues to generate. The thin dough membrane inflates like a balloon. Now let's understand why these spots turn dark brown or black. The Maillard reaction, which creates browning, requires temperatures above 140 degrees Celsius, but it accelerates dramatically above 160 degrees. The Maillard reaction rate follows Arrhenius kinetics. K equals A times exponential of negative activation energy, EA, divided by RT. For typical Maillard reactions in dough, the activation energy is about 100 kilojoules per mole. This high activation energy means the reaction rate doubles approximately every 10 degrees Celsius increase in temperature. At the locations receiving intense radiation, surface temperatures can exceed 200 degrees Celsius. At these temperatures, browning occurs in seconds. At cooler regions receiving less radiation, temperatures stay around 150 degrees. Browning here is much slower, taking 30 seconds or more. Let me give you some quantitative estimates to make this concrete. Hot spot temperature equals 200 degrees Celsius. Cool spot temperature equals 150 degrees Celsius. The ratio of reaction rates is exponential of negative 100,000 over 8.314 times 1 over 473 minus 1 over 423, which equals approximately 32. This means the hot spots brown approximately 32 times faster than the cool spots. This creates the dramatic contrast we observe. If a hot spot reaches full browning in 3 seconds, the cool regions would take about 96 seconds, well beyond the typical baking time. So how do we resolve this paradox? We need a complete thermal model that includes all the relevant physics. First, we must account for the spatially varying radiation field from the oven dome. This cannot be assumed uniform. Second, we need transient heat conduction within the dough itself using the full-time dependent heat equation. Third, we must include water vaporization, steam transport through the porous dough structure, and the associated latent heat effects. Fourth, we need to model pressure-driven expansion and blister formation using the mechanical properties of the dough. Finally, we incorporate temperature-dependent Maillard reaction kinetics to predict browning rates at different locations. The complete energy equation is density times specific heat times partial T over partial T equals divergence of K gradient T plus Q rad minus LV times dm over dt. When researchers implemented this complete coupled model in computational simulations, it successfully reproduced the Leopard spotting pattern. What are the broader implications of this analysis for baking science? First, at very high baking temperatures, radiation heat transfer dominates over conduction. You cannot ignore it. Second, spatial non-uniformity in the heating field creates the desirable texture and appearance. Uniform heating would actually produce inferior results. Third, transient effects like rapid vaporization and pressure spikes are essential to the physics. Steady-state models fail completely. Fourth, this is a true multi-physics problem coupling thermal transport, fluid dynamics, mechanics, and chemistry. No single physics model suffices. This understanding has practical engineering applications. Pizza oven designers can now optimize the dome shape and material properties to create desired radiation patterns and achieve consistent Leopard spotting. Dough formulation, particularly hydration level and protein content, can be tuned to control blister size and distribution. Hydration percentage equals mass of water divided by mass of flour times 100%. Neapolitan dough typically uses 60 to 65% hydration. Higher hydration increases water content, leading to more steam generation and more dramatic blister formation. Let's compare this with other types of baking to see what's unique about Neapolitan pizza. Typical bread baking occurs at 200 to 230 degrees Celsius. At these temperatures, conduction is more significant and radiation less dominant. Cookie baking happens at even lower temperatures, 170 to 190 degrees. Here, browning is slow and uniform, with minimal steam effects. Neapolitan pizza bakes at 480 to 500 degrees Celsius. This extreme temperature makes radiation dominant and creates the unique rapid effects we've discussed. Here's an interesting question. Could we achieve leopard spotting at lower temperatures? The answer is unlikely, unless we create extremely non-uniform heating artificially. The fourth power dependence of radiation means that moderate temperature differences at low temperatures produce small radiation differences. The radiation difference is proportional to T to the fourth minus T0 to the fourth. At high base temperatures, small variations in T produce large variations in radiation. Traditional Neapolitan pizza is made in wood-fired brick ovens. Does this matter? Yes, it matters. Wood fires create natural temperature gradients in the brick dome, with hotter regions near the fire and cooler regions elsewhere. The high thermal mass of the brick dome creates persistent hotspots that remain relatively stable during baking. The volumetric heat capacity of brick is about 1.6 times 10 to the 6th joules per cubic meter per Kelvin. This large value means temperature changes slowly. Modern gas pizza ovens can replicate these effects with proper burner placement and dome design to create similar non-uniform radiation fields. Let me return to one particularly interesting aspect. The steam expansion rates observed exceed predictions from simple ideal gas behavior. The ideal gas law predicts that for constant pressure, volume should be directly proportional to absolute temperature. V2 over V1 equals T2 over T1. For heating from 25 degrees Celsius to 100 degrees Celsius, this gives a volume ratio of 1.25. But experimentally, researchers observed volume expansions 3 to 5 times larger than this simple calculation predicts. Why? Because we're not just heating gas, we're converting liquid water to water vapor. This is a phase change with a huge volume change. At 100 degrees Celsius, the volume ratio of water vapor to liquid water is approximately 1700. 1 milliliter of liquid becomes 1.7 liters of steam. This enormous volume change during phase transition explains the explosive expansion of blisters. It's not just thermal expansion of gas, it's vaporization. Let me share some results from numerical simulations that validated this complete model. Researchers ran finite element simulations tracking temperature at over 10,000 spatial points in a 30-centimeter diameter pizza. The simulation used a time step of 0.1 seconds and ran for 90 seconds of baking time. The simulation results showed leopard spot patterns that matched experimental observations, both in size distribution and spatial frequency. The average spot diameter was 1.5 plus or minus 0.7 centimeters, matching measured values from real pizzas. Predicted blister heights were within 15% of measured values, confirming the accuracy of the pressure-driven expansion model. There's something philosophically interesting about this result. The fundamental equations of physics are uniform and smooth, yet they produce irregular, chaotic-looking patterns in the pizza. Small variations in initial dough thickness, moisture distribution, or oven temperature create large differences in the final pattern through nonlinear amplification. This means each pizza is truly unique, with its own pattern of spots and blisters. No two are identical, like fingerprints. Paradoxically, this apparent imperfection in browning is what makes authentic Neapolitan pizza aesthetically perfect. Uniform browning would look artificial and unappetizing. Let me summarize the key scientific points we've covered. Pure heat conduction models fail to explain Neapolitan pizza browning because they ignore radiation, which dominates at 485 degrees Celsius. Non-uniform radiation fields from the oven dome create localized hotspots that receive 2 to 3 times more heat flux than average regions. Rapid water vaporization at hotspots creates transient vapor pressure spikes that exceed 2,000 pascals in seconds, causing blister formation. Maillard browning reactions have strong exponential temperature dependence, causing browning 32 times faster at hotspots compared to cool regions. The complete explanation requires coupling thermal radiation, heat conduction, mass transport, mechanical deformation, and chemical kinetics. What broader lessons does this teach us about scientific modeling? Simple models like pure conduction are useful, but they have limited ranges of validity. Outside those ranges, they fail completely. The dominant physics can change dramatically with parameters like temperature. What matters at 200 degrees may be irrelevant at 500 degrees. Experimental validation using techniques like thermal imaging is crucial for testing theoretical predictions and revealing missing physics. Complex, irregular patterns can emerge from relatively simple physical laws operating in nonlinear regimes with spatially varying boundary conditions. Let me leave you with some final thoughts. This pizza problem demonstrates that sophisticated physics isn't just in particle accelerators or space telescopes. It's happening in your kitchen every day. Understanding the quantitative details of the physics doesn't diminish the beauty of a perfect pizza. Instead, it deepens our appreciation for the remarkable complexity involved. Science explains phenomena in terms of underlying mechanisms, but this explanation doesn't reduce the phenomenon to something less interesting. A pizza is still delicious whether or not you understand its thermodynamics. The best science combines mathematical rigor and quantitative precision with a sense of wonder at the beautiful phenomena the universe presents to us, even in everyday experiences like eating pizza.